In our lectures for today, we're going to address how the chemistry of EDTA as a chelating ligand is linked to how we design and execute an EDTA titration. Like any titration, a complexometric titration, which is a general term for a titration that involves complexation of a metal cation by a Lewis base. So EDTA titrations are probably the most common example of complexometric titrations. In a complexometric titration, like any other titration, the concentration of the analyte is determined by finding the endpoint volume and then taking the endpoint volume times the concentration of the EDTA titrant, remembering that EDTA binds all metal cations in a 1-to-1 ratio, will give you the concentration of the metal cation that is your analyte. In our lectures today, we want to show you how the speciation and equilibrium constant of formation and the conditional formation constant factor into the calculations related to and the prediction of the titration curve, which is what an EDTA titration is designed around. The reason we're interested in a titration curve when we're designing an EDTA titration broadly boils down to the idea that while EDTA has a large K sub F at almost any reasonably basic pH, it's important to know at any time during your titration how much free ion might still be present in the titration mixture, and to be confident that at your endpoint volume, the concentration of uncomplexed metal cation, which is your analyte, is indeed vanishingly small. So in today's lectures, we're going to specifically highlight how during an EDTA titration, we can use the conditional formation constant to calculate the concentration of free metal cation at any point during the titration. And the plot of the metal cation concentration versus the volume of EDTA added is broadly what defines the EDTA titration curve. In your first intro video today, we'll talk about the form and the shape of the EDTA curve and how it is graphed in a little bit of detail. It will be similar in some respects to an acid-base titration curve, but instead of pH, on the y-axis, we're going to have a PM measurement, where PM is analytical chemistry code for the negative log of the free metal concentration. So the capital M stands for metal. Remember, big picture, in your EDTA titration, your titration mixture, your titration reaction mixture is relatively complex because you have your analyte in its original matrix, you have your EDTA titrant solution with a known concentration being added, and you have an indicator metal ion, which initially is bound to the analyte and is then displaced by EDTA. So for instance, in your EDTA titration of natural waters, where your analyte was calcium or magnesium ion or both, initially in your reaction mixture, an indicator is going to be bound. The indicator is also a Lewis base that interacts weakly with the analyte cation. The indicator is bound to the metal cation, giving you a metal ligand complex with a certain color. When EDTA displaces the indicator, and that will always be favored at equilibrium due to the large binding constant of EDTA, the metal EDTA complex is colorless, and the release of the indicator ligand from the metal ion changes the color of the indicator and hence the color of the solution. So there's a lot going on in an EDTA titration matrix, and we want to use some of our equilibrium tools to help you decipher the underlying chemistry behind a successful EDTA titration so you can evaluate your own EDTA titration procedures or design your own EDTA titration procedure effectively if you ever need to.